go. Hello and welcome to Calculus. We are starting at chapter 2 and we are going to talk about limits. So, introduction to limits. We talked earlier about the parts of calculus. We said limits, derivatives, and integrals. We will cover all three in Calc 1. The chapter 2 is only about limits. Limits will give us base to define all others, derivatives and integrals. And they will give us also a way to compute some very interesting situations and also understand certain phenomena that surround us in the world. So the main thing here is, what is a limit? The formal definition will be given all the way back in 2.7, but the best informal definition for the limit and to understand the core of what the limit is this sentence. Limits compute y values of the function. That's it. So, limits compute y values of the function. Now you're going to, before you scream, hold on, we did that in pre-calculus. You plug a number and you're done. Limits operate differently, okay? And for that, we need to go and talk about examples. So now let me just give you the notation. The notation will be limit x approaches a of some function f of x is equal to L. So this would be our main notation for limits. Clearly, if you are allergic to something, you try to avoid it in life. I am allergic to students who do not write limit in front of the function where the limit should be written. So please, don't trigger my allergies. Yes?
This limit, would it be considered an operator?
Yes, very good.
Where would it land on the order of operations?
It's not an order of operations, it's a different animal. Operations are happening between numbers. Addition. 2 plus 3 is 5. It's operation. It works. Now, limit is operator just like derivative and integral. They operate on functions. So they're changing functions, they're computing functions, yes. So it's a different plane of, it's a step up from there. Great. All right, so now let's talk about the limit. I said, why would we have this if we can compute the y values using pre-calc? Let's put a pre-calc question down. Say f of x is equal to x squared minus 1. And I am interested at what is f of 3? Well, you would say, well, that's 3 squared minus 1, which is 8. And you understand that that creates 3, 8 ordered pair that you can graph. You understand that 3 is the input, 8 is the output. You understand that this is a point in space, on 2D space. You understand that from the functional definition that your rule was x squared minus 1. So you have all of that knowledge from pre-calculus. And you can put this on a graph. We have 1, 2, 3, 4, 5. This is called minimum effort. There we go. 7, 8. 1, 2, 3. 1, 2, 3. So we have this, this, and this, and then we have 2 and 4, so 1, 2, 3, 4, symmetric here, and then 4, 5, 6, 7, 8, 9, 9, and we snake through x squared. There we go. So what are we talking about? Oh, this is wrong. Is it? No, it's not. It's good. Because this is 1, 2, 3, 4, 5, 6, 7, 8. Good. All right. So what's the way the pre-calculus deals with this? Pre-calculus says, what is my input? Input is 3. That's here. You are supposed to draw a line, vertical line, up or down, to hit the function. So if we draw the vertical line up to hit the function, you will hit the function right here at 3, 8. It will bounce into 8, providing you y equals 8 answer. So we say that we know from pre-calculus that y is equal to f of x, and our x equals 3 input provides y equals 8 output. So everything that you see on the screen right now is pre-calculus. Now, what is the way that calculus deals with this? Well, calculus question will be, what is the limit of x squared minus 1 as x goes to 3? And as you are expecting, answer should be 8. Now, the interesting thing here is that this 8 was not computed by plugging in 3 for x. So how do we get 8? Well, calculus, remember what I said, that the calculus is a study of motion? Now, do we see a motion anywhere in this formula? Where would motion be in this formula? Where is the motion encoded in this formula? In? X approaching 3. In this arrow, that's the motion. You see, x goes to 3. X approaches 3. X is not 3. Do we all understand the concept? So x equals 3 means x is 3. X approaches 3 means x is going towards 3. It's not 3, it's going there. You see, I'm going towards the printer. I'm not at the printer. So this is x going towards 3, me going towards the printer. Me going towards the door, right? It's the end of the class. So x approaches door, x approaches printer, x approaches 3. So 3 is the location on x-axis, and x is going there. Now, how you as x can approach 3 on x-axis? Well, you can approach it from the left, or you can approach it from the right. So, red approach, I call this Juliet approach. We have all of these x values approaching 3 from the left. Now, would you agree that the y values of all of these x's that are marching toward 3 are climbing up this line, which produces y values that are climbing up towards 8? Do we all see that? I can draw a few of them here. Pew! That's one of them. We can draw another one. See that? So the closer I go to 3, the closer I climb to 8. Now let's see the Romeo approach from the other side. Blue. Blue for the boys, obviously, right? So we go down and we go down. Where do they meet? At 8. So we don't get to calculate 8. We get to infer 8. It's a trend. Your x values are marching towards 3, and the y values are marching towards 8. Now I have a very simple proof. It's a middle school level proof for this. We're going to do a chart of values, right? I'm going to put a 3 in the middle, and I'm going to assign, say, 3 values on each side. If you like pain, do 10. Which way do I approach 3 from the left? Let's use red for that. Well, let's say I am at 2.9. You can think of 3 as $3. Then at 2.9, I am 10 cents away, right? At 2.90. And then I go 2.99. That's closer to 3, right? That's 9 cents closer to 3. And then 2.999. You know when you go to a gas station? Yeah, they go to that precision. Yeah, right? The gas is 2.41 and then 9/10 of a cent over there. Please ask for change next time you're there. I do every time. When I moved to the United States, I stopped by the gas station, right? And I saw 9 over 10. I said, ooh, fraction, right? Being the geek I am. And I asked the person, well, what is the 9 over 10 over there? They didn't know, actually. So it took me a few times to find someone to say, oh yeah, that's 9/10 of a cent. I never seen a denomination smaller than a penny. So obviously, where's my change?
Right.
Where's my change? What do you mean you round up? I've seen Office Space. I know what you guys are doing, right? Someone is cashing in 100,000 or 200,000 a year on a side, right? 9/10 of a cent. Well, here we go, right? We are using that method now. We want to go to 3, so we go at 2.9, then 2.99, then 2.999, and that gets closer and closer to 3. On the other side, for the Romeo, we have 3.1, 3.01 to get closer, and then 3.001 to get closer still. So this is how you would approach using numbers, right? A bad approach would be to use 0, 1, and 2, because those numbers are really far. They're infinitely far. I mean, any of these numbers are infinitely far away, because you can always fit infinitely many numbers in between any 2 numbers. But a lot of interesting stuff can happen between 1 and 2, I guess, and then less should happen between 2.999 and 3. Now you take your abacus and you compute all of these red and blue values in your function x squared minus 1. Why are you looking at me? Go. Compute the values. I will be computing values as well. All right, so all the values are already there. You can discontinue your calculations and just cheat off of the, the board. Do we see what's happening with y values? What can you tell me about red values? Where are they going? They go towards 8, right? You see that it's $7.41, and then it's $7.94, right? There is a jump of 50 cents there. And then it's $7.99, so it's getting closer to 8. Now, how about blue ones going towards 3? They fall into 8, right? So, if it walks like a duck and walks like a duck, it's a 8, exactly. Yeah, it's an 8, right? Now, I hope you are not disappointed, but this is it for limits. That's the entire story of Chapter 2 and Calculus for Limits. We will get fancy with functions and things because we can, like mathematical gymnastics. But as far as the concept goes, what they do and how we can calculate, this is where the story ends for all of calculus forever. You have a way to approach from two sides and then observe what's happening with numbers as you are approaching, and at the same time as you are approaching, your y values might hit the same number or they might go apart, right? You can have that as well. We say no limit. And this is the end of the story. Believe it or not, this is it. Now, the first thing over here is called graphical way to find limits. So you can find limits by looking at the graph. You can find limits by computing values in a chart. Let's say you decide never to learn how to graph a function because you are refusing to memorize what is the shape of square root of x or ln x, right? You refuse to do that. Can you still be successful? Yes, because you will always have ability to pick x's, compute y's, plot the points, and connect the dots, just like in the coloring book, right? So you will always have that middle school method available to graph functions. And let's say you never learn anything about any of the functions in terms of the graphs. Pick x's, compute y's, and then just draw the line through those points. You're done. The limits. You decide to disregard the entire chapter 2. Can you find limits? Yes. It's going to be annoying to compute all of these numbers every time, but it clearly can be done. So the chart method is that ultimate method to find the limit. It's annoying, so we don't do it. But if you are facing a limit that you don't know how to solve algebraically, the graph would be too annoying to draw or whatever, you can always go back to chart. Now clearly we will resort to technology, right? Your cell phone has access to the internet. The internet has, let's say, Wolfram Alpha on it or whatever else you decide to use. So you can always do that. But the chart is, believe it or not, where it ends, right? You don't need to learn anything else. But now we have more chapters, more sections in this chapter coming up that will teach us how to find these limits algebraically, how to deal with infinities, and what are all other cool things that we can learn from that. So there is a lot of value packed in the rest of the chapter 2. But that's it for limits. So now what happens if these numbers don't match? Well, clearly they're not going to meet at the same point on the y-axis, right? Just like Romeo and Juliet did not meet that final time at the same time, at the same place, and they immediately resorted to suicide because that solves all problems immediately, obviously. Yeah, you have no issues after that. It's not a public service announcement, but it's but it's true, unfortunately, right? So these y values can meet, or they end up at different numbers, in which case we claim no limit. Now the red ones, the ones that I call Juliet, would be approached from the left. And as a notation, you will say x approaches a minus. You put the minus in the exponent of a. The blue one is approached from the right, and that one will have plus. And now I'm going to assign values over here. So we can say it's approaching, let's say red one is approaching m, and the blue one is approaching n. We are going to write a major theorem about this now. This is extremely important theorem. If limit x approaches a minus of f of x is the same as the limit x approaches a plus, which is from the right, equal to some L, then the overall limit x goes to a of f of x is L. Otherwise, limit does not exist. So this is your first major theorem of Calculus 1, and this is what solves problems. Here's an example. What is the limit as x approaches 0 for 1 over x? Okay, I can draw the graph because I know what the graph looks like. And now I'm going to stare at this graph and decide what's happening as I approach from the left, which is red, which would be limit x approaches 0 minus of 1 over x. So what's happening with y values? Where do they go? Yes? Only one way. Negative infinity. Very good. So the y values will shoot to negative infinity because it's only the approach from the left. So you are writing this function right here. You have nothing to do with the other side of the graph. Remember, you can't go through the vertical asymptote. We'll talk about that in more detail, but right, this is it. Now what's happening for Romeo? Approaching from the right, which is the limit x approaches 0 plus 1 over x. Where is he going? Positive infinity. So what is the theorem telling us? Yes, there is no happy afterlife for these two. One went to negative infinity, one went to positive infinity. See? That's something that you didn't get from the story until you took calculus class, right? Limit x goes to 0 of 1 over x does not exist. Left limit and right limit do not agree. let's work on another example of the similar kind. Say your function f of x is piecewise function. X plus 1 if x is larger than 1, and negative x squared if x is smaller or equal than 1. What is happening with the limit as x goes to 1 of this f of x? So what is the limit as x goes to 1? Yay! Let's graph piecewise function. So we start from, we make the partition. I usually draw this orange line at 1. That's not an asymptote. That is just a partition to separate two worlds. The world before x is 1 and the world after x is 1. Because that's where domain breaks. So what rules the world after 1? Well, it's x plus 1 function. X plus 1 function will start at 1, so it will have open circle and go 45 degrees forever this way. So this is our top line. It's function x plus 1. Now you can actually plug in 1 here and note that the first point that you have to draw at 1 is 2. So your function is starting at 1, 2. So this is 1, 2. And it's going to have a 45 degree slope because your slope is 1. 1 over 1. So rise 1 to the right 1. And it will go from there. The second function is negative x squared. Now, negative x squared has the vertex at 0, 0. And it's going to open downwards because it's negative. But it can't pass the barrier, right? Because after 1, it's the linear line. So we get to draw this. And now we can remove our orange line, construction line, right? And we have our piecewise function graph. So now I would like to see what Romeo and Juliet are doing over here, right? Are they going to meet or no? So Juliet approach, limit x approaches 1 from the left. And the left side is the quadratic function. So this is f of x. So we will follow quadratic function as we are approaching 1 from the left. So as you are approaching 1 from the left, where is the y value going? That's wrong. Negative 1. It's negative 1. So do we all see that as you are approaching 1 from the left, you are coming from the left? You are coming from the left. You are walking towards 1 all the way, right? So as you are walking from the left, going towards 1, where is the... Where is the y value going? So you are going down this line, right? Which means the y value is going towards wherever descends, and that's at negative 1. So we conclude that the limit, right, is going to go down this line and it's going to end at negative 1. So our limit is going to be negative 1 for the red approach because we are approaching from the left. Now we are approaching from the right. That means we are going down this line. Where is that going to end up? X approaches 1 plus. It approaches 2. Every time, the answer of the limit has to be the y value. So what is the y value for the point at 1 as we are approaching from the right? It's approaching the height of 2. So what do we conclude? Limit does not exist. Very good, because they do not have the same value. So theorem says, and this is why it's important to learn the theorem, right? It's the theorem is the one that teaches you that if the limits are the same number, overall limit is that value. Like we had 8. Remember? Walk like a duck, quack like a duck, it's 8. So that's the one, right? Both numbers, red and blue, came up to be 8. Therefore, the overall limit is 8. Now, one number is -1, the other number is 2. That's the second clause in that theorem, which says if the numbers are not the same, then the limit does not exist. Now, same question, same function, same graph, different limit. Limit at 3. Limit as x approaches 3. Limit exists. If you are approaching 3 from both sides, what's happening? You are looking at 1, 2, 3. You are looking at this value here. Do we agree that it's going to be 4 from both ends? As you walk left towards 3 and you walk from the right towards 3, they will be squeezing in this way, squeezing in that way, and they will end up at 4. So this is case by case. It is not function by function. Depends which point you are approaching. So if I'm approaching at 1, bad things happen, right? This continues there. But if I'm going to approach any other number, in this particular case, it's going to work fine. Now, I want to go back to my 1 over x graph. Do we see that this function has no limit only at 0? Every other value will be cool, because you will be able to approach from both sides, pick any value, anywhere. It doesn't matter. Like pick this. If you pick that, you approach from the left, you approach from the right, they meet at this point, which is that value there, a half, -1/2. So you would have a limit in that case. So you can't learn the limit by memorizing, oh, it's 1 over x, limit does not exist. No, limit does not exist only at one point. Limit exists at all other points that you can possibly compute. So you have to do the approach from each side and then either visually conclude, looking at the graph, or do the chart of values. And then you will see that. So that would be the story of limits. These guys, where is the one that here. These guys over here are called one-sided limits. You will see that in the book. So one-sided limits. So approach from the left is minus, approach from the right is plus in notation. And we will be using this in our next lectures, the minus and plus notation. So you need that. And then you have your definition, which is the one that your theorem that we are using to calculate these limits, to say overall limit is, let's say 8, or overall limit does not exist, depending on what the left and what the right limits do. That's it. Yes?
Can you say again what the one-sided limit is?
These are the one-sided limits. These two. So one-sided means you're just approaching from the left.
I see. So
Or-
one side and then the other side.
Yes.
Two one side.
So yes, so you have two one-sided limits, one from the left, one from the right. That's what it is. Questions, concerns? Well, that's it. I hope you're not disappointed. Bye.